Okay, the next lecture is dedicated to a continuation of the study of recurrence and transience of Markov chains. We will continue our investigation into criteria when we can say that the Markov chain is, or certain states are transient and recurrent, and we will present this famous theorem of Polya from the 1920s, which says that the simple random walk on the Euclidean lattice is recurrent in dimension 1 and 2 and is transient in dimension 3 and higher. That's a very famous classical result of standard stochastic process theory, and it shows that from a probabilistic point of view, there's a huge distinction between 2 dimensions and 3 dimensions. These differences will appear in other fields of physics or mathematics as well, for instance in quantum field theory and other fields, and it is ultimately related to the properties of the Green's function, which is absolutely fundamental, of course, in many aspects or many fields of mathematics. So here we already see that space dimension 2 is really a fundamentally different case as space dimension 3, and that's kind of an interesting result, although you wouldn't see it immediately why this difference is so profound. And then ultimately we will focus on the question of the existence of dynamical equilibria for these Markov chains. So when you think of a physical system which is described by a Markov chain, you would probably want to see whether there is some sort of a dynamical equilibrium, as I said, to some statistical dynamical equilibrium, some kind of statistical or distribution on the collection of states, which will not change after all in the long run. This is the question for equilibrium distributions, or as you would say, invariant distributions on the collection of states. Of course, this is very important from a physical point of view. It is, as I just said, related to the long-term behavior of these systems. We will investigate and we will construct such invariant distributions, and basically will characterize the situations when these invariant or statistical equilibria, when they are unique, and how we can represent them in terms of kind of easy computable or kind of computable observables of the Markov chain. All this is the contents of the next lecture, which is about to start now. Welcome to lecture 6 of our lecture series on stochastic processes. We will continue with our study of Markov chains. And I guess this is going to continue for at least 2 more lectures after this. And the lecture today will be dedicated to the completion of our first look into recurrence and transience. We will present the famous result by Polya about the recurrence and transience of simple random walk on the Euclidean lattice. And in the second part of the lecture, we will discuss invariant distributions, which is a concept to describe long-term statistical equilibrium of Markov chains. Okay, let's continue first with our study of recurrence and transience. Recall that a process was called recurrent if the probability of return in finite time, strict return in finite time, when starting in that position is exactly 1, else we call the process transient. And we had the proposition in the last lecture that a state is recurrent if and only if the powers of the transition matrix, when evaluated on the corresponding diagonal element, are not summable, which is the same as saying that the probability for infinitely many returns, or for infinitely many visits of the state, by the state starting in I, that the probability of this is 1, and which is the same as saying that the probability of an infinitely many returns is just positive, because the opposite case is transience, and in transience case we know that the probability of infinitely many returns is 0. So in the end we only have these 2 different possibilities. So therefore a positive probability of infinitely many returns already indicates that the probability in fact is 1. Okay, this is where we were, and we want to apply these criteria now to the cases, or to the famous case of the simple random walk on the Euclidean lattice. But before we do so, we want to introduce the concept of irreducibility of a Markov chain, or which is, to be honest, more a property of the corresponding transition matrix for a Markov chain. So a Markov chain is called irreducible if for all states I and j, for all pairs of states I and j, there exist certain powers n and m, which in general will depend on the chosen states I and j, such that the, say, n-fold power of the transition matrix evaluated at coordinates I, j is positive, and likewise some power, here power m, of the transition matrix evaluated on position ji of the matrix is positive. So these formulas simply say that there is a positive probability of correction. There is for each paths, or for every pair of states I and j, there is some power, or some number of time steps, such that in this given number of time steps, the chain travels from state I to travel j with strictly positive probability. And vice versa, we also want to assume that for every ji pair of states, so if you ask for the converse, for the converse direction, there is some power, some finite power, such that the transition or journey from j to I will happen with strictly positive probability. In this sense, the two states I and j are connected. They see each other in the sense that from I can travel to j in finite time with strictly positive probability, and from j I can travel to I in finite time with positive probability. Now, if for all pairs, all possible chosen pairs of points in the state space enjoy this property that one can be attained in a properly chosen number of steps when starting from the other, and vice versa, when this is the case, you call the entire chain irreducible. So irreducibility means that in some sense the state space does not disconnect in different parts, where once you are in one of those parts, will not communicate with one another. And here a Markov chain is said to be irreducible if all states communicate with all other states in the sense as described above. And in the future, basically, we will discuss only the case of irreducible Markov chains, because if we have a non-irreducible Markov chain, which means a reducible Markov chain, basically then we can subdivide the entire state spaces into pieces, which then will consist of irreducible segments or parts, and then we can do the analysis on each of these irreducible patches and later discuss the question of how we put the things together. But in most of the cases, this is not any question of real interest. Because effectively, on the long run, what you see in this case is just different Markov chains which live on different state spaces and which on the long run are completely disconnected. Okay, so here's our first application of the concept of irreducibility. And then if we have an irreducible chain, so all states communicate with one another, then all or no states are recurrent, which means that if you have one state in your state space and the chain is recurrent, then all states will be recurrent. Well, why is this so? We have this criterion about the powers of the transition matrix, and we will apply this now. Now, suppose J is recurrent, and we want to check recurrence of I. Then we can look at the powers, the transition powers of a certain order, n plus k plus m here, where k is the actual variable power that we want to look at. And then this probability here is a probability of transition from I to I back to I in n plus k plus m steps. And obviously this is bigger than you ask for the probability of precise transitions from I to j in n steps. So you use the first n steps to make a transition from I to j. Then you make a loop transition from j to j in k steps. And then finally, with the remaining m steps, you go back to I. This is a sequence of probabilities which by Markov property provide a lower bound for the probability for the entire thing to happen. In fact, you have many more possibilities to go from I back to I in n plus k plus m steps, but this is certainly a subcollection of paths which will do the job as well. And the probability for all of this to happen, for all these possibilities, is certainly bounded from below by this number. And if you choose n and m so that these probabilities which appear here, are strictly positive, which you can by irreducibility, this gives you an interesting or reasonable lower bound, namely this sum of all these powers from transitions from I to I will then be bounded from below by the corresponding sum of k powers, which is then sandwiched between those fixed k and m power of the matrix K. Now, since these numbers which are on the left and on the right are strictly positive, the object on the left, on the very left side, must be infinite if the sum, which is in between those k and m powers, if that sum is diverging. So therefore, if the state J is recurrent, which is indicated by the non-summability of this sum of matrix powers on the diagonal, then the state I will be recurrent, and so forth. So this is a simple and straightforward application. And we can see that we would probably need to struggle a little bit more in order to arrive at the same conclusion here if we didn't have this analytic property at our disposal. So here again I have this remark that we typically consider only irreducible Markov chains, because else we can basically decompose the state space into equivalence classes when we say that two states are equivalent if they're exactly communicating in the way that I had just described. This is then an equivalence class. And then you can decompose your Markov state space for your Markov chain into irreducible subclasses. And basically, on the long run, your process will arrive in one of those classes. And then you can do all the analysis that is interesting for you. And most of the analysis of Markov chains on the long run goes into long-term behavior, and all the analysis on the long-term behavior will be an analysis in a respective component of this state space. So therefore, in the future, we will basically consider only the case of an irreducible Markov chain anyway. Now, another consequence of this simple analytic condition that we have derived for characterization of recurrence is that every irreducible Markov chain on a finite state space is necessarily recurrent. That's a simple exercise, and I will put it on the exercise sheet. We will now come to the famous example of simple random walk on the Euclidean lattice, which is a very fundamental object. It is already pretty much very, very good approximation of what we will later call Brownian motion. So it is kind of a model for a molecule which moves in space, but for technical reasons, say, we chose to discretize space. And for instance, we could think of a molecule which is just walking on the Euclidean two-dimensional lattice. And so at each moment of time, it makes a decision. So it jumps on these nodes of the integer lattice. That's the state space. And whenever it arrives at a certain point, it makes a decision whether it should go left, right, or up, down. And then it does one of those two choices with equal probability. That is what we call the simple random walk on the lattice. This was the picture for 2 dimensions, but of course we can also draw a picture for higher dimensions. Then the thing can go north, south, east, west, and up, down, or whatever. So the transition probability, the one-step transition probability from x to y, is 1 over 2d, where d is dimension, if x and y are connected. So in other words, if the 2 points x and y differ in only one coordinate and by an integer jump in, by an integer change of 1. That's when we call the 2 points connected on this graph, if you like, of the integers, of the integer lattice, and that's our transition probability. So in each dimension, you can consider this object. This will be now a discrete in time and discrete in space stochastic process, which has a countable state space, so the integer lattice is countable, but it's an infinite state space. And we would like to give now the statement, and we would like also to indicate the proof of Polya's theorem, which is from 1921, one of the first really famous highlight theorems of stochastic process theory, which says that simple random walk on the integer lattice is recurrent if and only if the dimension is 1 or 2. So in dimension 3 or higher, the simple random walk is transient. But obviously this is quite a dramatic difference of the behavior of a simple random walk in dimension 2 or 1 on the one hand, and dimension 3 and higher. So if you think again about this story that I told about the ship that sets sail and is leaving the harbor to go out for some fishing or something on the ocean, then you would, like here in this case, it would mean that if the ocean is two-dimensional, then eventually the ship will come back each time. So whenever it sails out, it will come back with probability 1. And hence it will have infinitely many returns. So if the ship is nicely maintained and it can go out for fishing the next day, it will, and it will return. But in the three-dimensional case, so if you have a submarine, if you like, that can go on the surface but can also dive or can even get elevated, then the submarine, if it behaves in a completely random fashion, and assume the submarine, as I just said, is also a rocket, so it can go up in the sky, so then the submarine, if it just behaves in a random fashion, it will return a couple of times, but eventually it will not return anymore, because three-dimensional space is so big that eventually it will get lost out there in three-dimensional space. So you see, we have a dramatic difference here in the properties of two-dimensional and three-dimensional space. Three-dimensional space is profoundly bigger than two-dimensional space. Just as a side remark, you can think of also lattices or lattice structures which somehow interpolate between a two-dimensional and a three-dimensional lattice, and there you get, this will be discussed probably in a little later, then you will have very interesting and fine results regarding the asymptotic, regarding the precise structure of these interpolation spaces, whether you have recurrence or transience. So here we have a very important difference between, so the recurrence and transience really measures how big a space is, and in a way it's an invariant, which is a very nice and very interesting quantity to study about spaces which probably have less symmetries than Euclidean space. Okay, how do we prove this result? Well, we know from what we did before that we basically just, if you like, have to study the iterated powers of the transition semigroup. So here we have a matrix in the end, and we have to just take the powers of this matrix. However, if you do high matrix powers, then things can become messy. Here we use what is called the local central limit theorem. Well, by parity, by the way, only only even integer powers of the matrix can contribute. So you ask yourself, you start at 0, what's the probability to return to 0? And you need an even number of steps. If you leave, you have to make a decision in a change of coordinate, and basically you have to unwind this change of coordinates in another direction, or possibly in another order, but ultimately you would need to have a return back to the origin is possible only in an even number of steps. So therefore we have to look only at even powers of this transition matrix, which I had just defined. And then we can use what is called the local central limit theorem, which is, in the one hand, a combinatorial problem. That's one way to look at it. But there are more efficient ways to do it in this combinatorial way. Anyway, so we consider these powers of the matrix, and the local central limit theorem tells us that if we can normalize these powers, or we have to multiply these powers by a certain function which depends on dimension, namely if n is the power of 2 to the n is the power 2n is the power which we want to study, then if we multiply by n to the d half, then this has a positive limit, which is this universal quantity on the right hand side. But this means in particular that these powers p to the power 2n are of the order of 1 over d half, correction, of n over d half. This is exactly the important information that we need, because if we insert this into our analytic criterion about recurrence and transience, then we have just seen that this asymptotically behaves like 1 over n to the d half, and we see that if d is 1, we get 1 over square root of n, and if d is 2, we get 1 over n. This is also the harmonic series. In both cases, we get a divergent series, and here's a misprint, obviously. So this is a divergent series. If d is 1 or 2, and if d is 3 or higher, we get 1 over 3 halves, for instance, if d equals 3, or 1 over n squared. These will all be then converging series. So therefore, by our analytic criterion, we have exactly this case of recurrence and transience, depending on dimension. This local central limit theorem that we use here will be dealt with also in the exercise sheet, when we will give a hint or a sequence of hints how to establish this result by not combinatorial but analytic statements. This very famous and important example concludes our first look into the question of transient and recurrence. We will encounter the question a little later again, but from a different angle. But I want to emphasize that the question whether certain geometric graphs are recurrent or transient is a question which is investigated in the science literature intensively even today, because many combinatorial structures emerge nowadays in all kinds of theoretical and practical applications. For instance, in network theory, you could ask whether certain networks are transient and recurrent, or in theoretical mathematics, certain groups can be given an interpretation of a graph, and then you can ask whether the group is recurrent or transient. So there's a huge amount of interesting examples of graphs which appear, and then the question whether recurrence or transience is true is a first approach to measuring the size of these structures. So if you like, in both cases, like in the Euclidean lattice case here, we had, of course, two types of countably infinite structures, but the question whether such a structure is recurrent or not is ultimately, as I just had indicated, a question about the geometric properties of these things. So it's a concept of size which is finer than just countable. And it's a very interesting question which is really active, a matter of active research still today. We will now start to look into what is called invariant distributions or invariant measures for a Markov chain. This has to do with the long-term behavior of the chain. So we have now learned how to set up a chain, how to construct it. We have conducted a first investigation into the long-term behavior in terms of recurrence and transience. This is, of course, ultimately a question about the long-term behavior. But now we want to have a more macroscopic description of the long-term behavior, and you would like to ask whether there is some statistical description about the average states, if you like, in which the chain will be after a certain amount of time has passed. So the question is, will there be a distribution on the states which will be attained by the Markov chain in equilibrium when time goes to infinity? Is there some kind of dynamical, statistical equilibrium that the chain attains? Okay, And I recall a proposition before we actually give an answer to this question. I recall a little proposition that essentially we had already in one of the previous lectures. Namely, it goes like this. If you have a lambda p Markov chain on some countable state space, so it starts with initial probability lambda and then is proceeding according to a according to a step distribution, which is described by the matrix P. Then the distribution of the Markov chain after k moments of time is described by the vector, which is obtained by taking the kth power of the transition matrix, taking the transpose of this, and applying the initial vector lambda to that, applying this transpose to the lambda vector, which was the description of the initial distribution of the state. Okay, why is this true? That's now easy to prove. We want to compute the expectation of this chain after k moments of time. We want to describe the statistical distribution. This is just the same as basically knowing what this integral is, the expectation of any observable applied to the chain at time t, at time k, and taking the expectation of this. Because this is then the integral, or this is just the evaluation of the function f against the distribution of the chain at time k. So by our general chain rule, if you like, this characterizes this integral. Basically, is exactly the integral of f against this distribution, which we want to describe. Now, by what we had already seen, our linear algebra kind of calculations for Markov chains, this is the kth power of p applied to the vector f, and this is then taken in the inner product with the initial vector lambda. That's our linear algebra style representation of this expectation. But we want to understand what's the action of all this on the function f, so we just take the transpose of the matrix of this kth power and move it onto the other side of this Euclidean inner product, and we get the representation that we want. So in other words, the kth fold iterate of the matrix transposed applied to the initial vector lambda is the distribution of the vector at time k. In particular, if you make only one step, then the distribution after one step that we obtain if we started with initial distribution lambda is p star lambda. That's the distribution. So let me write it out again to you. So p star lambda, you ask yourself, what's the probability? So p star lambda, let me write the formula first. If you evaluate this at a position k, this is what? This is the sum over p jk times lambda j. This is the transpose of the matrix pkj, now pjk. You sum this over all positions j in the state space. That's the transpose of the matrix P applied to the vector lambda evaluated at position k. And what does this sum here tell you, or how is it to be interpreted? It is what? So you ask yourself, what's the probability to be after one step in position k? And this is what? It is the sum over all probabilities to start at some position j in state space and then make a one-step transition from j to exactly this position k where you want it to be. So this is this formula for in the case when k equals 1. When k equals 1, this is our correction. K here appears now twice here in my notes. That's probably a bad choice of notation. Let me therefore say it again. So you want to know, so suppose you have a state which you call S, then you want to know what's the probability to be in state S after one moment of time if at initial time you started with initial distribution lambda. So then this is the formula. So you take the sum over all possibilities that take you to position S in one step, namely you sum over all starting states J, which are possible. You take the probability that you actually do start in that state, that's lambda J, and then you have to multiply this with the one-step transition probability to actually do the jump from that J to S in one step. That's this formula here, which is in this proposition in the case when I have k equals 1, when I do a one-step thing. This is P star lambda. And now comes the definition of an invariant distribution. We say, a lambda vector, if you like, a lambda vector of initial probabilities, is called invariant if the P star operation operating on this lambda doesn't change the lambda. Which says, okay, lambda is such a wonderful starting distribution that if I do one step after this starting distribution, then the new distribution that I see of possible states is just the same. So a reshuffling, you can interpret the Markov chain in terms of how it operates on distributions. You feed into a certain initial distribution, then this initial distribution is reshuffled according to this random stirring mechanism, if you like, that the Markov chain does, and then you get a new one. And in general, it will be different than the one that you started with. But if you were lucky enough to put in a starting distribution that does not change through this process, then you call this thing an invariant distribution. So if you have a positive vector, apart from the probabilistic interpretation, you could interpret this equation here as a linear algebra equation. Namely, it says that the vector lambda, if you interpret the function lambda as a vector, it says that you have a vector lambda which is an eigenvector for eigenvalue 1 for this adjoint matrix P star. And this is not any eigenvector. What you want is that this eigenvector has positive entries. So in general, when you have a non-negative eigenvector, whenever you have a non-negative vector which has this stability property, then you call it an invariant measure. And if this wonderful vector has the additional property that it is also summable, then you call it not only an invariant measure, but you call it an invariant distribution. So we have to be a little careful with the language here. A non-negative vector, which is an eigenvector for the adjoint of the transition matrix with eigenvalue 1, is called an invariant measure. If the entries of these non-negative entries of this possibly infinite vector in an infinite state space case, if the entries of this vector are even summable, then we are even happier, and we call that not only an invariant measure but also an invariant distribution. Of course, we think that an invariant distribution or an invariant measure for a Markov chain has some sort of asymptotic stability with regards to the dynamics of the process, in the sense that it will not only be preserved over time when we start with this distribution, but we also would like to see in some proper way, in some way which we will formulate a little later, that the average behavior of this process will tend towards such an invariant distribution. So we really think that the invariant distribution captures a large amount of the essential long-term behavior of the process, and that's why it is so important for us to understand it. The next proposition is the first non-trivial result here in this segment, which says that if we have at least one recurrent state in the state space, then we can construct at least one of such invariant measures. And the construction goes as follows. So fix this one recurrent state, and then use it to construct a function on states as follows. For each state I, you consider the number of visits that the chain is doing when it was started in the position K before it returns back to position K. So you count the number of visits that the chain is paying to state I, and you take the expectation of this when you start the chain in the recurrent state K. You count the number of visits before you return to K. You start in K and you take the expectation of this number of visits. This is a function which depends on the state I, on the state to be visited, and as a function of I, we now claim that this is an invariant measure. So obviously, it is non-negative, and what we want to show is that the adjoint of the transition matrix leaves this function, which we interpret then as a vector, invariant. Okay, first little remark is that by recurrence of the state K, we have with property 1 return in finite time. So therefore, if we count only the points including the first arrival time in K, but not 0, then we see that this sum for each path has exactly one moment of time where we count a visit to the state K itself. So if we insert I as the state K itself, then we see that in the sum we have exactly one evaluation which contributes here for each path. So therefore we get 1, the constant 1, which we integrate. So therefore gamma kk is a 1. Okay, now let's consider an arbitrary state in the state space. And what we want to show ultimately is that this gamma ki is the same as if we apply the P star matrix to the gamma vector and evaluate at I. This will be our conclusion. We want to show that this funny function which we had just introduced, so this counts of visits, this average count of visits, this function has the property that it is left invariant. It's invariant for the matrix P star. Okay, that's a little bit of a computation. So we start out by writing again the definition of this. This is just writing out the definition again. And we can take out the sum which is taken, we can write out the sum which is taken with up to this stopping time tau k. We can write it in slightly different form by writing a complete sum over all integers, but where we have the indicator function that this index L is less or equal than the indicator. This is just the same. Now we write this sum, which is a sum with respect to the index L from 1 to 2. We write it as a sum from L equals 2 to infinity plus the first summand. The first summand is, so in all cases here we have just sum of probabilities here, so since we are taking expectation of indicators. So the first summand is x1 should be an I, then that's the condition that's written here, and the stopping time should be no more than 1 should be less or equal than the stopping time tau k, which means what? Well, that's obviously that's in a way it's a redundant condition, or it's a condition which is always true. So the stopping time by our definition here is always greater or equal to 1. Okay, I was hesitating in the previous moment because it is, if I define it like this, is by no way obvious that tau k is really bigger or equal to 1. And in fact, in my definition of this gamma function gamma ki, which I just introduced, I should better write here the strictly positive hitting time. In this case, my previous claim is just correct, as well as the claim that this gamma function, if I evaluate this in the location when I equals k, is in fact 1. And in this case, the argument that I had just made is namely that the stopping time tau k plus is bigger or equal to 1 is always true, is then just correct. So let me write here the plus all over the place in order to make sure that everything is properly defined and consistent. Okay. Right, so if we work with tau plus, then we see that this is always strictly greater or equal to 1. So therefore, this constraint here is no condition. We have just a plain transition probability here that we are in state I after one step when starting in k. This is pki. This summand here is a pki, and we can of course write this pki also with a pki times gamma kk, because we had just seen that gamma kk is just a 1. Okay, that will be the second summand in this decomposition that we had just done here. Now, the other summand, the first summand, is now the sum from 2, L equals 2 to infinity regarding times, and I can now decompose this event, which is here taken in the probability, into the sub-events according to the state that was assumed at time L minus 1, so at the time before L, when I look into this. Okay, so this sum is a sum under the condition that the stopping time L, this correction that L, the moment of time L, when I evaluate this, is so that the stopping time tau L tau plus k is below, that this time L is below the stopping time, which in other words says that up to moment time L, I have not visited the state k for the first time after leaving from k. And this means that this sum here is a sum where the state k in position j cannot appear. So therefore this sum can also be taken as a sum over all states j without the state k, because else this condition here would be violated. Furthermore, by conditioning on this past here, I see that if I know already that I have not visited the state k up to moment time L and before, and if I then additionally ask whether I'm at moment L in position I or not, this is just asking for the event which is described here, and then under this condition asking whether I still make a transition from position J to position I. So therefore, by the Markov property, I can decompose the probability for this chain of events into a probability for the condition, which is described in these two events up to moment of time L minus 1, times the probability of a transition from J to I. Note in this argument where we have used the Markov property, in fact we have used the following additional consideration, namely that if we know that this set J is unequal to K here, the condition that we haven't seen the state k up to a moment of time L is the same as saying we haven't seen the state k up to a moment of time L minus 1, because at the moment L minus 1 alone, we already know that we haven't seen the state k anyway, because j is unequal to k. So therefore this condition that's written here is in fact the same as this condition here, and this is now really a condition which on all its beauty is a condition only on the behavior of the path up to moment L minus 1, and therefore this application of the Markov property here was admissible and was correct. But if we look at this expression here, we see that this is pretty much the expression that we had in the previous representation of this gamma function, but now there is this time shift that we start this evaluation at times L minus 1, but the time shift here is offset by the fact that we start the summation at a later moment of time only. So therefore, if we plug this sum into this sums, or this summation into this sum of probabilities on the right hand side, we see that we end up with this gamma function, but now for the state j. The pji transition probabilities were appearing before, so if we sum this all together, we see that we get this application of the matrix applied to the vector gamma, where one summation is missing, or one index is missing in the summation, but this is exactly the index or the summand which we had isolated in the first step of our consideration. So in the end, we see that in fact this vector gamma that we started with is invariant under the action of the adjoint of the matrix P. So we start now to investigate whether this found invariant measure, which we have just constructed, could possibly be unique. And for that purpose, we have one or two lemmas that we want to state and prove. First lemma is that if we have a recurrent state and P is irreducible, then this vector which we just have constructed is really non-trivial in the sense that it's nowhere zero and it's nowhere plus infinity. Why is this? Okay, we choose an arbitrary point in state space I, and by invariance we know that the gamma vector is invariant under the action of the adjoint of the matrix, and so therefore it's also invariant under the action of powers of the adjoint of this matrix, or which is the same as it's invariant under the adjoint of powers of this matrix. So therefore gamma I is the same as pji in the power m multiplied by gamma jk. Now we recall that by invariance there is a certain power that produces a positive matrix entry k at positions ki of p, and that's the power we choose here in this equality. Then since this is a sum of non-negative numbers, this sum is certainly an upper bound for one of those summands, and we choose as the sum with index j equals k, so we end up with this expression on the right hand side. But here we have gamma kk, which is a 1, and here we have this transition matrix. So in particular we have a number which is strictly positive, and therefore gamma ki is strictly positive. To show that we have that this gamma k vector is not plus infinity, we evaluate this gamma vector at position I equals k, and we again know by invariance that this has this representation through an application of a matrix in the right power in the adjoint fashion. And here we choose the power n in such a way that the transition from I to k is is positive. For here we could probably write j first for all j's, and then we take a bound by a single j equals I, which gives this expression. And now we have seen that that this number here, the power n, was chosen in such a way that this number here is finite. So in particular, we can divide by this number, and using the fact that the left-hand side is equal to 1, we obtain the bound that this gamma ki guy is less or equal to this inverse ratio of this transition matrix entry to the power n, which tells us that the number on the left-hand side cannot be plus infinity. Okay, that was one lemma. The next lemma says that if we have an irreducible chain, then every invariant measure is trivial, or else it is strictly positive. In fact, this statement here is not a corollary in the strict sense of the previous assertion, but it follows by an argument which is exactly the same, or as in the previous case. Namely, if you look at the previous argument, the only thing which we really have used, or the only two things that we have really used, is the fact that we have one position, namely position k, where this gamma vector has a positive entry, and then from the invariance of this vector and the irreducibility of p, we have been able to conclude that this invariant vector must be strictly positive everywhere and cannot be finite anywhere. So we can apply exactly the same argument to any invariant measure, which leads us to conclude that if we have an invariant measure which has somewhere any positive entry, then the whole thing must be positive everywhere and finite. And here's an example for a situation when you have no non-trivial invariant measure, which is the so-called escape chain. I will not discuss this example in this lecture in full detail, and I rely on the fact that you will look at it yourself. But it is a simple chain with infinitely many states, of which you can show by elementary algebra that they cannot have a non-trivial invariant measure. So when you have a set of equations for this invariant measure, which is deduced from the equilibrium condition, which then will allow you to conclude that there cannot be a non-zero invariant measure, and therefore they cannot have any recurrent state, because if it had a recurrent state, we could do the previous construction as before, which would give us an invariant measure which would be non-trivial. But we can conclude by elementary algebra that this chain does not admit any non-trivial measure, so therefore a recurrent state cannot exist. And since this is a chain which is also irreducible, it shows that the entire chain is not recurrent but transient. And that's why it's called the escape chain. The next assertion is the last one, which we need in order to conclude that in the irreducible case, up to multiplicative constant, basically, we have only one invariant measure. And this next proposition is the key technical proposition to prove this. Namely, it says that if you have an invariant measure which at some position is 1, say, at some state k is 1, then our constructed vector gamma with this state k as a reference state is less or equal to this lambda vector everywhere. So it shows that this gamma k vector is the minimal invariant vector, or the minimal invariant measure among all invariant measures, which are normalized in such a fashion that at position k, at this state of reference, they are 1. Okay, why is this true? Okay, that's an inductive argument, or we give an expansion of this lambda j for an arbitrary state j which is unequal to k. We give an inductive expansion which shows that the inequality that we claim is actually true. So we start out with this lambda at an arbitrary position j, and we write out again what it means for lambda to be invariant. It means that in this position lambda j, which is the probability to be in state j, is the same as starting in any position L from the state space and doing a one-step jump from L to j. So that's what it means for lambda to be invariant if we evaluate this invariance at position j. Now this is a sum over all states, and we can decompose this sum into the summand which corresponds to L equal k, to this state of reference, and to the sum of all remaining states. Now, at position L equals k, the lambda factor is a 1 by assumption. So therefore, just this transition probability remains. And it remains on the other sum, the full factor, the full product of the two factors. Now, the first term we keep it as it is, and the second one we do another expansion in the same way as before, but now for the lambda L. So knowing or using the fact that lambda is invariant, we can write the lambda L. Now I replace the L by an L1 because I need more than one L indices. So I will work now with a collection of L indices, which all will be basically running through all the states of the state space. So now this lambda L1 here can be written as a lambda L2 times the probability of a transition from L2 to L1. So that's the L2 summation here, which I have introduced. This factor PL1J was unchanged, and I have rewritten the lambda L as a sum which involves a summation over all L2 in the state space. This I again decompose, this innermost sum I decompose into the sum that I obtain. Correction, I decompose by fixing L2 to be equal to K, which means that I get one summand here, which corresponds to L2 equal K, in which case the lambda part is a fixed 1 again, so I get the product just of these two transition matrix entries. And then I have the remaining double sum where also now the second index, L2, is unequal to K. So here a little bit of a typo. Okay. Now, if I look into these terms, I can give them a probabilistic or a direct interpretation in terms of events. The first probability, or PKJ entry, just describes the probability to make a one-step transition from K to state J. The second product of probabilities describes what? written in the right order, it describes the probability of a path that starts in K, makes a transition to a state L1, and then makes a transition to J, where this sum is taken as a sum over all possibilities for states L1 except state K. So, in other words, this describes the probability for a path to start in K, do one intermediate step anywhere except K, and then end up in position J. And this can be described by writing the event like this. It's the probability of a two-step transition from K to J without visiting the state K in the intermediate step, which means that the hitting time of the state K should be bigger than 2. And now I can iterate this whole thing. So this lambda L2 I can now decompose, or I can write again using the invariance of lambda as a sum with respect to a third index L3, where I get one case when the index L3 is exactly K again. This is the situation when lambda L2 is a straight K. And then I get another factor in this expansion, which is a P L3 L2 transition. Correction, it's a P K L2 transition. It's this term here, which I obtain here, and I get the corresponding remainder of this sum of the expansion, now involving a full summation over this third index L3, where all the previous terms appear. This will be then the starting point for the expansion on the fourth level. But if I observe this, or if I take a look at this expression here, I see what? I see the description of a probability of a path which starts in K, makes a transition to a state L2, which is supposed not to be K. Then I'm making the transition from L2 to L1, where L1 again is not supposed to be K. And then finally I make a transition from L1 to J. And this is nothing but saying, or it's just nothing but the probability for a three-step transition from K to J, but where I have not visited the state K before. Okay, so you see how it works. So we iterate these expansions and expansions, and so for all possible levels of expansions, if we just at some point ignore the remaining part, we have a sum which is certainly bigger than this corresponding sum of probabilities. That's correct for any level of expansion up to which we want to conclude or want to conduct this expansion. And so we see that the initial lambda j quantity with which we started is an upper bound for this sum for all levels m. But if I take now the limit of all these sums of all these events, I exactly get this infinite sum here on the right hand side, which by our definition of the gamma vector evaluated at position j is exactly this quantity. So we see that in fact lambda j is greater or equal than this quantity here on that. Correction. Lambda j is greater or equal than our gamma vector in an arbitrary position j. This proposition tells us, the proposition that we have just proved tells us that this gamma k vector is the minimal vector, minimal in a pointwise sense, among all possible invariant measure vectors which share this normalization to be equal 1 in the point of reference k. And this is now the key to prove the uniqueness. Namely, if P is an irreducible chain, then in fact this gamma k vector is the unique invariant measure for this transition matrix P. Of course, we assume here that K is a recurrent state. Okay, why can we conclude now in this fashion? Namely, if we have another invariant measure, which is not trivial, then there is at least one state where we have positivity. At least we have one I in which this lambda I is strictly positive. Now, by irreducibility, we know that it is then therefore everywhere strictly positive. It's one of the lemmas we just had. So if there is an invariant measure, and if it is not totally trivial, and if our chain is irreducible, then this invariant measure must be strictly positive everywhere. So in particular, it is strictly positive in the state K, and therefore I can pass to the normalized version of my lambda vector, which is now lambda bar, which is obtained by lambda by dividing all entries by the scalar factor lambda k. Or in other words, I just divide or I multiply the whole vector by the scalar number 1 over lambda k. This is my lambda bar now, and obviously lambda bar at position k is now equal to 1. Okay, now I do have an invariant measure which is non-negative and which at position k is normalized to be 1. So therefore, by the previous proposition, I know that there is a misprint here, that gamma is less or equal to this vector lambda bar. So this inequality sign here is the other way around. This inequality sign is like this. So therefore, if I pass now to the vector eta, which is defined to be the difference between lambda bar and gamma, then this is a non-negative vector, because I have taken at each position I have taken a difference between lambda bar I, and gamma, but I had just argued that gamma is minimal, so therefore at all positions I, this gamma guy is no bigger than lambda I, and therefore this eta I is a non-negative. It's a vector with non-negative entries. But being an eigenvector for a matrix, for a given eigenvalue, that's a linear property. So therefore the difference of these two eigenvectors is again an eigenvector of this adjoint of the matrix P. So therefore the whole thing is again an invariant measure. It is an invariant measure which at one position has a zero entry, because at position k this eta, but by construction, is 0. And hence by the previous lemma, which tells us that an invariant measure is either trivial or strictly positive, we know that we are in the trivial case, which means that the whole eta vector is the 0 vector, which means that lambda bar and gamma are everywhere the same, which means that the arbitrary lambda and the given gamma, they differ in each coordinate only by a unit, by some constant, which is everywhere the same constant. So, in fact, we have proved that if we have an irreducible Markov chain and a recurrent state K, then this then this constructive invariant measure is unique up to multiplication with a scalar factor. So here we could be already quite happy about what we have achieved. We have introduced the concept of an invariant measure, and we have seen that in the case of an irreducible recurrent Markov chain, we have a constructive method to obtain an invariant measure, which is basically the expected number of visits of the chain when we start and stop at this recurrent state. However, this construction is not so intuitive, and we have a much more intuitive representation of this invariant measure when we have an additional requirement or an additional constraint to be satisfied, which is that of positive recurrence. And this concept of positive recurrence of a chain will be an amplification or a strengthening of the condition of recurrence. Namely, we call a state of the Markov chain positive recurrent if the expected mean hitting time, strict mean hitting time, is finite. So we take the same strict hitting time as before, which we took as the basis for the definition of recurrence, and now we do not ask whether this return is happening in finite time, almost surely, but we want to take the expectation of this time it takes to return, and we want that this expectation is finite. So if tau plus I was a non-negative random variable, which was asked to be finite for the recurrence before, we now ask even more. We ask that this positive random variable has also a finite integral. That is more to ask than just asking whether this random variable is finite almost surely. We also want that it is even integrable. So therefore, positive recurrence is a stronger condition than just recurrence. And the final theorem of today's lecture is the following, that gives us a very nice representation of the invariant distribution of a chain in case when it is irreducible and positive recurrent. The statement goes like this. So if P is an irreducible Markov chain on a countable state space S, then the following properties are equivalent. Namely, all states are positive recurrent. This is the case if and only if at least one state is positive recurrent. So it sounds similar as in the case for recurrence. So either one state is recurrent. That's the correction. Namely, recurrence or transience is a property which is shared simultaneously by all states, provided the Markov chain is irreducible. And here, this is a similar thing with the positive recurrence. So positive recurrence is a property which is shared simultaneously by all states of the Markov chain, provided the chain is irreducible. So either of those two properties is equivalent to the case that there exists an invariant distribution, not only in invariant measure, and this invariant distribution then is unique, and it allows the representation as the mu I or pi, the value of the invariant distribution at position I, is just the inverse of the expected return time. And this distribution is then also uniquely determined and uniquely defined by this. Okay. An irreducible chain is positive recurrent if and only if the invariant measure, which is unique up to a multiplicative constant, is not only a measure but is also a distribution. So it is summable. It's a measure with summable entries. And in this case, the uniquely determined representative among all these vectors, which are the same except for multiplicative constant, there is a distinguished representative of all these vectors, which is the vector which is normalized in such a way that the sums over all entries is equal to 1. this vector will then represent exactly a probability distribution on the collection of states, and the entries of this probability distribution are given by this intuitive ratio. It's just the inverse of the time it takes to come back to this state. So the invariant distribution, if you like, the statistical equilibrium for a given state is the inverse of the time that it takes to return to this state if you start from this state. We want to prove this statement. The claim is an equivalence of three different statements which are all logically equivalent. That's what it says. Obviously, assertion 1 is stronger than assertion 2, because if all states are positive recurrent, then of course at least one is positive recurrent. So let's prove now that the positive recurrence of at least one state produces the statement that the invariant measure which we construct using this state is actually summable. Okay, let us then take this positive recurrent state. As we had argued, positive recurrence is stronger than recurrence, so therefore the state in particular is recurrent. What we are interested in is the sum over all the entries of this particular vector, because we want to check whether we have a summability here. Now, we take the sum over all these entries of these vectors, which means we take the sum over all states from the state space, and we insert also the definition of this function gamma ki, which was the number of visits before the stopping time tau appeared. Now, if we interchange the two summations regarding the time index L and the state space index I, we end up with this formula here. And we see that if we take the sum over all states I here, then we have, regarding the first condition here, a decomposition of the Shor event, which means that the sum over all i's here just produces an almost Shor fulfillable condition, or in other words, we can neglect this sum and neglect this condition, which is formulated here, and arrive at this formula here, which is only the summation regarding the time index and regarding the condition that the time index is no bigger than the hitting time to tau k. Now we finally use a lemma from elementary probability theory, which tells us that for a non-negative random variable with integer indices, with integer outputs, the expected value of this random variable can be written as the sum over all these probabilities for super level sets. So, in other words, this sum here is nothing but the expectation of this hitting time, of the strict hitting time, and we were assuming that this is finite. That's exactly the positive recurrence of the state k. So hence we have that the state k is positive recurrent if and only if the summation over the entries of this invariant measure, which we construct by means of the recurrent state k, is finite. Okay, now once we know that this sum is finite of these entries, we can give it a name, call it z. This is then, as we had just said, this expectation of this hitting time, and therefore we can now pass to an invariant probability measure, an invariant probability distribution, pi, which is obtained by normalizing with this constant. So we divide all the entries by this common constant z, which therefore trivially produces a new invariant measure or a new invariant vector whose entries then sum up to 1. So it's a probability distribution, in fact, on the set of states. Before we were not considering this special case, we were not asking for such a condition to be fulfilled. We were just talking about invariant measures where the summability condition was not considered at all. Now we consider this summability condition, and we had made a connection between the summability condition and the positive recurrence of any state. Okay, so K is positive recurrence, so therefore we can do the summation of the entries of this gamma K vector, and that's then finite, and we can normalize the gamma K vector to eventually be a probability distribution on the collection of states. And since at the particular position when I equals K, we know both enumerator and denominator particularly well, and in the enumerator we just have a 1 by construction of this gamma K vector, and in the denominator we have the Z, the ZK normalization constant, which we had also been able to write as this expectation of the return time. So we see that at least in position K, the claimed formula is correct. And finally, for K prime unequal to K, we know by, if you like, by irreducibility that K prime is at least also recurrent. So therefore we can construct this gamma K prime vector that will be also an invariant measure. And we had convinced ourselves that all invariant measures are the same up to a multiplicative constant. So it's a non-trivial invariant measure, so the multiplicative constant is strictly positive. And therefore, the summability of the entries of the gamma K vector translate into the summability of the entries of the gamma K prime vector. So these two vectors at first sight are very different because they are constructed in terms of hitting times of correction. They are constructed in terms of mean numbers of visits for a chain which starts and ends in position K or K prime. So these are very different quantities a priori. But by uniqueness of invariant measure, and since this is an invariant measure, we can conclude that they must be the same up to a multiplicative constant. So they're linear dependent, in other words. So therefore we can do the same invariant measure construction as before, or invariant probability distribution construction as before. We can consider this gamma K prime vector and divide by the normalization constant ZK prime, which will be also an invariant probability measure. But two invariant probability measures need to be the same, because the constant that relates the two must be the same, because both sum up to the same number 1. So therefore pi prime must be the same as pi for all I, and in particular for k prime, for I equals k prime, we have that this pi of k prime is the same as pi of k, but by construction pi of k prime is 1 over the expected return time to k prime when we start at k prime. So therefore for any other k prime, if you like, or for any other prime, we have the same representation, and the property 3 or the claim 3 is proved. Now, to go from 3 to 1, that all states are positive recurrent, this is just the same as what we had just done before. We just use essentially the uniqueness up to multiplicative constant of the invariant distribution. So there is the proof here will be just the same, and we'll probably give it as an exercise. Okay, so the statement again says, if we are in the convenient situation that we have an irreducible Markov chain, which is not only recurrent, but positive recurrent, then all states are positive recurrent, and we have a particularly nice representation of the invariant probability distribution, which is given by the inverse of the mean return time to the respective state. And this invariant probability measure is not only a measure, but it is really a probability distribution, which means that this is really an assignment which can be interpreted in terms of a starting probability. A general invariant measure, which is a vector which is not normalizable, is not a probability measure in the conventional sense, because the total probability of all states is not 1. But in the case of positive recurrent chain, we also have a perfect invariant starting distribution. We conclude this lecture by returning back to the simple random walk on the d-dimensional lattice. We have convinced ourselves that in dimension 3 and higher, the state is not a correction, the chain is not recurrent. And here in the second part of the lecture, we were mainly dealing with recurrent states. But what can we say about the recurrent situation in dimension 1 and 2? Well, in dimension 1 and 2, by the symmetry, this whole thing is shift invariant. And if you write down the equations for the invariant measures that you could try to find, you find very quickly that there can be only one invariant measure, which is no surprise that there's only one by irreducibility. We know that up to multiplicative constant there can be only one. And we can convince ourselves easily that the constant measure, which gives to every position in the d-dimensional lattice equal weight 1, is an invariant measure, and again by multiplicative uniqueness up to constant, the unique invariant measure. At the same time, obviously, if we sum the constant 1 over all integer positions over all lattice positions in ZD, this gives a plus infinity. So we see that we have a non-trivial invariant measure, but this is not an invariant distribution. We have no summability here of the invariant measure. And we can talk about the invariant measure in the sense that up to multiplicative constant, this is unique. So this chain, the Markov, the simple random walk in dimension 1 and 2, which is an irreducible chain, has an invariant measure, but this invariant measure is not an invariant distribution because it's not summable. So therefore, the Markov chain, by our previous result, the simple random walk, is recurrent, but is not positive recurrent, because else the invariant measure would be summable. So the simple random walk in dimension 1 and 2 returns in finite time almost surely, but the expectation for this return to happen is infinite.